So thanks to the organizers for inviting me to give a talk, and it was a great workshop and a summer school. I thoroughly enjoyed being here. I'm going to talk about analysis of a particular kind of decoding of Reed-Muller codes, and I think maybe the first talk in this workshop or so doing with Shannon model instead of the Hamming model. Okay. So we do an analysis of decoding, which became famous in the last, I think it appeared around 2019. And I'll also tell you why it is quite interesting, let's say. Right? So this is joint work with my collaborator, Arvind Rameshwar. He is a research fellow in IUDX ISC. A quick recap of Reed-Muller codes. We are going to deal with binary alphabet. So an nth order binary Reed-Muller code is an evaluation of all multivariate polynomials whose degrees at most are, and we know the length, which is 2 power m, and the dimension, m choose less than or equal to r, and the minimum Hamming distance 2 to the m minus r. So all these properties we know of Reed-Muller codes, so I will not touch upon them again. And what has been shown in recent times in the context of Reed-Muller codes is that one, they are capacity achieving for the binary erasure channel. So this is work by Kudekar et al. So they use some monotonicity results and sharp thresholds of Boolean functions, etc. Then there has been more recent work by Reeves, Pfister, and Abbe-Sandon, which showed that Reed-Muller codes are capacity achieving for binary memoryless channels, in particular binary symmetric channel 2, right? And we also know that the Reed-Muller codes are close cousins of polar codes. Again, so after that, seeing the connection itself, and we know that polar codes are capacity achieving. So that's the reason this quest started. And there has been very good progress in that direction. So that is one part as to capacity achieving results. But in the capacity achieving results, it's always a ML decoder which is assumed for proving the capacity of Reed-Muller codes. What is known about decoding algorithms for the Reed-Muller codes is, again, this is a very short literature review of, there are many, many more, but I'm just highlighting the important ones. So the Reed's majority logic decoder itself, which was way back in 50s. And then there was a decoder for second order Reed-Muller codes, which view them as bilinear forms and take some projections and try to infer matrices relating to that. So that is like, the set of 2 works there. And then there is Doomer's recursive decoding, which is based on Plotkin decomposition of Reed-Muller codes. And this has had analytical results too. Even the previous ones had. This had analytical results, but this works for any R in general, and that is more or less, I could say, the state of the art for many, many years. When this new algorithm by Minier and Abbe, which came in, the conference version came in 19 actually, in ISIT, it's called recursive projection aggregation. And I'll describe the decoding algorithm. And what we have done is provided an analysis to that of this particular decoding algorithm. So in RPA decoding, the recursive projection aggregation, there are 2 steps. One is projection and the other is aggregation. And this kind of happens in iterations. So what happens in the projective step? By the way, I always, again, I'm assuming a binary symmetric channel. And so these BIs, the evaluation points is a vector space, right? F2 to the M. So I'm looking at the collection of all k-dimensional subspaces and calling them this BIs, the set of BIs, right? And what is meant by projecting a code, a receive vector onto a coset of a particular BI is this operation, right? So you're looking at the coset, the corresponding coset which contains X, right? And then we are just summing the Y's corresponding to that. Okay, so this is like projecting Y onto a particular coset, but then of BI. But then if you want to say what is the code word corresponding to that, then I project it onto all possible cosets of BI, right, for some fixed ordering of the cosets. And so this is what happens for the receive vector. If we look at the noise-free versions of it, then the exact projections are actually code words of Rm, M minus K, R minus K. Right? So this is an easy fact that is proved in the paper. I'll not state more than that, but that is crucially used in the projection step. So that is the projection step in the recursive projection aggregation. What about the aggregation step? So this aggregation step was not something which was ever done in, let's say, Reed-Muller. So projection step was done always in some form or the other while doing decoding. But then the aggregation step was never done before. So what is aggregation step? So for all the points, for each point, what we look at is that so anyway, so this NKM is a set of all, so that's the cardinality of BI in some sense. I mean, that set of collection of all k-dimensional subspaces, I'm denoting it as NKM, right? So what we are doing is that in every projection, a particular coordinate is going to correspond to one coordinate in the projection, right? And that happens for different subspaces. All the subspaces, a particular coordinate will be there in one particular position. And it is actually taking part as if it were an XOR, right? So what we are seeing is that if whatever we have decoded, right, after projection, assume there is a black box decoder, right? Black box decoder for the lower order. So somehow we have a Y hat, right? And if whatever estimate you get from Y matches the estimate of Y hat, we do an upvote. Otherwise, otherwise we don't count. It is on the zero side, right? So this way, we are just, again, kind of doing majority in some sense. But for that particular bit, we are seeing how many subspaces it is kind of agreeing with the estimates in the lower dimensional subspaces and how many it doesn't. If it agrees more than half, you don't flip the bit. If it agrees less than half, we'll flip the bit. So that is the decoder. Okay? So this is the aggregation step. So now what is the recursion part? So the recursion part, I'll just show you in the form of a tree. So this tree is picked from my paper, but just that it goes all the way, you can assume that this goes all the way to first order Reed-Muller codes. Okay? So in this tree, it's a rooted tree. Assume that the noisy code word which we obtain for Rm, M, R is sitting here. And every time we are doing a projection, we are going down the tree, right? And every time we are going a projection, we are going all the way up to first order, right? And then every time we are doing an aggregation, we are going up the tree. So that is what we will be doing in this projection aggregation tree. So in the recursive projection aggregation, what happens is, so suppose if this were just a second order, right? So there'll be only one stage. And once we hit the first order, we know a ML decoder. The ML decoder for the first order is n log n complexity. It's a fast Hadamard transform decoder. So that we know how to do. Okay. So assume this is second order. What is done is that, so we go to first order. Every time we do decode using the FHT decoder here and aggregate and get an estimate for the second order, right? And this you keep. So there was a Y, now it changed to something else, right? But you don't stop it there. The reason is because in the aggregation step, we are deciding on each coordinate independently, right? So it's not necessary, first of all, that it be a code word at all, right? But the thing is that we allow for some number of recursions. So once we do the aggregation step, then again you project, and then again you do the aggregation and keep doing it. Okay? And for rth order, keep doing it. And for every time you go up, there'll be iterations. And for every time you go up, there is again coming down many times and going up many times and so on. So that is the recursion part. Okay. So this is the recursion projection aggregation algorithm. And why is it interesting? So this is what is the performance which was shown in Ye and Abe. And what it shows is that actually recursive projection aggregation, vanilla version, kind of, is better than, again, here I'm seeing, maybe I'm not, looking at the right plot. Yeah, that's fine. So it is actually close to ML. That is the key takeaway. RM without list is very good. With list, it is like close to ML. Okay. But this is for second order kind of Reed-Muller codes. Okay, because the moment we hit third order or fourth order, let's say if you hit fourth order, it becomes extremely hard to implement any of these decoders for Reed-Muller. Right? So that is the reason this is done for second and third orders, let's say. And RPA shows very promising performance. So, but then there is no analysis whatsoever of the decoder until our work. Okay. So what is our main result? Is that we prove an upper bound on the probability of error. Okay. So in the projection step, I showed k dimensional subspaces. So first we will analyze for one dimensional subspace projection. So every time we are reducing the dimension, by one, r by one or m minus one, r minus one, that's what we are doing. Okay. And if we use one dimensional subspaces for projection, so there is a particular upper bound on the probability of error. N is 2 power m, r is a parameter that we already know, and epsilon is something which is which is something like half 1 minus 4 p bar times 1 minus p bar. Okay, so this is for a general R. I will just show a sketch of proof of this for the second order, and then I will just flash the results for general R, right? And how to interpret this result is that if we kind of plug in R's, which grow as log m, still the probability of error actually goes to 0. Okay, so that can be verified. So what we are saying, so that this actually doesn't give constant rate Reed-Muller codes, whose performance under low complexity decoder probability of error goes to 0. That's not what we are claiming. But for log m, we do get probability of error which goes to 0. Okay. So analysis has two components. One is analyzing the FHT decoder, and the other is analyzing the aggregation step. So in the FHT decoder, so one assumption which is generally done in all these decoders for linear codes is that you assume that all 0 code word is transmitted and then analyze the probability of error. It is the same for all the code words. So that is the thing. So key ingredients are these two. So if we go to analyzing the FHT decoder, so I'm just going to introduce some notation. It is like we are going to, so let's say we are analyzing second order. I did the projection, I'm at the first order, and I have to do analysis for the FHT decoder, right? So if I have a y which is Bernoulli p, then the projection will have a Bernoulli which is 2p times 1 minus p. That is one. The second, the projections, we are going to map it to plus minus 1 instead of 0, 1, okay? Using regular normal mapping that we have. So now the FHT decoder can be thought of as if I'm taking inner products of this y, okay, with a bunch of functions which are given by this chi s of x, which are minus 1 per x, the inner product of x and s in the 0, 1 world, right? And we have to look at positive and the negative separately, just because in the Reed-Muller code, there is a constant term also, right? So in the linear functions, when we look at it, there is no constant term. But in the Reed-Muller first order, there will be a constant term. So we have to look at this and minus separately. So the ML decoder can be written as R max of, the received vector, taking the inner product with all these chi s functions. Okay. So now what we are doing is that, again, I have transmitted all 0 code word. Then even after projection, it remains an all 0 code word. So then how does it concentrate as an inner product around for the chi 0 term, right? For the chi 0 term, this inner product, the way you can look at it is that it's going to add all possible, the error vector, which is binary 2p 1 minus p, right? So that is the thing. And that is going to add all in, incoherence in some sense, right? So it's all going to add, right? And when we have independent random variables, all of which you are taking the addition, concentrating an average per se, concentration around the mean is very easy. You are just applying Hopkins. So that is easy part. Okay. So we are going to say that how it concentrates around this in plus minus epsilon. Okay. What about the next part is we look at the concentration around chi s, right? So for any other chi s, what is going to happen is that half of the terms are going to add and half of the terms are going to subtract, okay, in the noise term. Okay. So there is a subtraction of two terms, okay, each of which are somehow concentrating around its mean. Okay. So if you look at the inner product, that is going to concentrate around 0. So if you look at how it concentrates around 0, we just get an upper lower bound, okay, in terms of just saying, yeah, the, we call this alpha 1, alpha 2, but then we want, the difference should be less than or equal to epsilon. But then this also, we will just lower bound it by saying alpha 1 in a particular range around beta and alpha 2 in a particular range around beta. So if you take those difference, it will be anyway within epsilon, right? So that is a lower bound. And this one is like, again, concentrating around the mean. So we are using Hovdings. Okay. So what, after these two, like we got a concentration around chi0 term, and we also got a concentration for chi-s term. So putting these two together, what we can get by union bound kind of arguments is that we can somehow make these intervals disjoint. Okay? So if we are able to pick your epsilon such that these intervals are disjoint, then there is a clear winner for the maximum, right? So we are going to do that and say that if the intervals for chi0 is this, the minus chi0 is this, and the others are this, and if epsilon is within this range, then the maximum will be the term given by chi0, right? And that happens with a very high probability. The reason is n is sitting in the exponent, and the pre-log factor, pre-exponent factor is not dominating anyway, right? So this is the analysis for FHT. So then we realized Berneshev, Dinur, they had an analysis for FHT decoder for the first order Reed-Muller codes in a very, very different way back in 2006. But we didn't know till we derived our result. But then what we saw that approaches were very different, but the exponent here still matches exactly. So the pre-exponent factor may change, but the exponent matches exactly. So we were happy with this analysis. It's just a 2-slide analysis. I think their analysis was somewhat longer. Okay. So that is the FHT decoder. What about the aggregation step? So in the aggregation step, what we assume is that the first order we have decoded correctly. Okay? And that we have decoded correctly for all the n-1 subspaces that we have. Okay? That also just gives me a pre-exponent factor of n-1. That's all. Okay? So we are going to always condition on this event, right? So if I condition on this event and then look at the law, which was doing this flipping kind of a thing, right? So y cap is always 0. So then what happens, this factor is what I am writing it as px here. Okay, it's the sum of yx plus b plus x plus bi. The x term is going to stay the same in all the n-1 terms. This other term is always going to change based on the subspaces. Anyway, okay. So rewriting this as if yx equals 0, it is the sum of some terms, and if yx equals 1, it is the sum of some other terms, right? So what we are effectively want to say is this one concentrates, or normalized version of this quantity, concentrates around this random variable, which we are calling phi bar infinity. Okay. Again, nothing but law of large numbers or Hovdings that we want to say, right? You will get one particular thing for yx equals 0, which is this term, and for yx equals 1, this one. Okay. So the catch here, though, in the aggregation step, okay, is that this concentration is in particular true for all these yxs and yx plus bi. Okay. But what we want is conditioned on G, how does that behave? Okay. And conditioned on G, how do these random variables behave is not clear. Whether they concentrate or not is not clear, right? So that is what is the other gap that we close. It is that upon conditioning, we still show that phi bar. So there is one more step. We have shown that phi bar is close to phi infinity. Again, close in the probability sense. So there is a particular, inequality of probability which is coming into play. But if two random variables are close, we also show their indicators are close. The indicator of that greater than half, those are also close. Okay. But then we also want to show that they are close even after conditioning on G. Okay. The G is the probability that all the first order things were decoded correctly. Okay. What happens is once we condition on G, there can be correlations between whatever is happening on the previous side. Okay. So we kind of get across that by proving a small inequality, which makes use of the fact that this G is a very high probability event. Okay. So that is one of the key catches, because that was the main bottleneck to proving the analysis of RPA. Always there is this dependency between, there is a correlation between several random variables which is coming into play. Okay, so that's what we show. So which means that once these are close, it is true that whatever we are going to flip is going to be this random variable, but then that flip random variable is exactly equal to your y. Okay, that's what we show in asymptotics. Flip random variable is actually equal to your received vector. But then if the flip is equal to your received vector, once you flip it, it becomes 0, right? So what we have shown in this whole thing is that in a single iteration of the RPA, our probability of error actually goes to 0. So we are not even using multiple iterations of RPA. Okay? So because in the second iteration, we can't use this fact anymore, we will break down, because even the y-axis will have several correlations. So because what happens in the second iteration of RPA is y is the new estimated y, right? So if I have a new estimated y, they will have correlations in the noise, right? So that is the reason right now we are at a stage where we can't analyze this algorithm for the second iteration. We can't do it right now. Okay, so that's the analysis, and if you combine the analysis of FHT and aggregation, we get a bound. Okay, so then we could use this bound. So the way even this algorithm works is we go to the last stage for a general R. We go to the last stage. Only in the last stage we analyze the FHT, but then every other stage is only aggregation. Okay. So whatever analysis we did for one step of aggregation, the same analysis carries out back to the root node. Okay? The same analysis every time you're going to condition on the previous layer being conditioned correctly, analyze the aggregation step, and then you get that in one iteration somehow the previous y also is 0, and you keep going all the way up to the root node, right? And if we do that, this is the probability of error expression that we get. Okay, so that completes the analysis for higher order. I'll just take 2 more minutes. That's it. So for the analysis of higher dimensional projections, okay, so the analysis that I showed you was for one dimensional projection. Every time I'm doing a projection by dimension, I mean like just taking, the subspaces BIs were subspaces of dimension 1, right? But the RPA algorithm also allows for multiple dimension, projection, right? So or higher dimension projections. So here also it's like, again, the FHT step is going to be the same, but if you go back and see the aggregation step, it's going to be different in the sense that if you look at phi x, it's going to be a quantity, right, which has correlations. So earlier it was like clean sum of y-axis, which were all independent random variables, so we could use Hopdings. Okay, but now what happens is each term in the sum of that 1 to n tilde, whatever it is, whatever it means there, they have correlations. Okay, so these are all sums of, functions of independent binary random variables, but they have correlations. Okay, so we can't apply Hopdings directly, but we could get an inequality which works. Okay, so we got a more general concentration inequality from Raginsky and Sesson in their book monograph, right, which says if I have a function of n independent binary Bernoulli random variables, right, and the concentration about the mean goes by, is upper bounded with this value, p is anyway from here, alpha is the slack that we have, but there is a quantity called CF, which is the Lipschitz constant of the function that we are going to deal with. Okay, so the previous phi x, whatever we saw, for that, if we are able to get an estimate, or if we know the Lipschitz constant, and if it is good enough, then it is good for our purposes. Okay, so what we kind of quickly argue, it's not very hard to argue that Lipschitz constant for the function that I showed you before is a Gaussian binomial coefficient. Okay, it is n k minus 1 m minus 1, but it is this, the number of k minus 1 dimensional subspaces sitting in a m minus 1 dimensional space. Okay, and that is my Lipschitz constant. And if we incorporate this constant and try to apply the previous inequality, then I get some, again, a probability of error which is very high and so on. So, but again, the catch is we were hoping that if we do higher dimensional projections, somehow maybe we get a better exponent, because exponent is the one which kind of determines whether how fast it's going to 0. Like it will give improvements with respect to log m. So exponent doesn't improve that much compared to one-dimensional projection. Okay. So what are the open problems? It's like, ignore the first one. The open problems are, I would say, the third one, which is like, we want to show probability of error, which goes to 0 for R larger in some sense. See, we don't want to achieve the capacity, but somehow we want to show for RPA, for even, let's say, positive rates or something better than log n, my probability of error goes to 0. Okay. The main problem seems to be, the main bottleneck based on the analysis seems to be that if you keep doing the projections, you are actually increasing noise in every projection. Okay. And the more you do it, in the last step, the noise is like quite bad. Okay. So whether that will take us to anywhere positive rate or not is not clear right now, but we are still to work on it. Okay. And then we want to do it for list decoding. We have some ideas for general BMS channels. On the first part, it is like, so taking all the possible subspaces is somewhat wasteful. You can actually do parts of subspaces, but analysis kind of goes through. Okay. So these are our results, and this is our RCAP paper. Somewhat old, but we will update with the more newer results of higher dimensional projections too. And I'll stop here.
Questions? Nick.
So, if I understood correctly, there's only empirical evidence for RPA performing well when
yes.
small.
Yes.
Do you think it's possible that when R is like much larger than log n, that maybe the noise that you get
possible, but that is not clear. So the reason is that the noise getting added, it is getting added very heavily. Every time you do a projection, you're increasing noise quite a bit. So I can't conjecture this way or that way. Not very clear at all. Yeah. Yes. Yeah.
One of your slides showed that colors we can outperform polar.
Yes.
Even polar course with
CRC. Yes.
So my question, whether these algorithms are practical, because I think, so what's the decoding complexity?
So the decoding complexity for this is n to the R log n. So in particular for, n reasonable and let's say n2, 3, etc., it's quite reasonable that we can run it for the lens of interest.
So my main question was, can we replace polar codes with modern?
Very much possible, I think so. But see, the thing is, there are two things to it. This already is a, kind of high complexity decoder for 6G, right? So n to the R log n kind of. So there are two questions. One is to reduce the complexity of this, but then I'm not sure if we'll be able to show good results analytically, right? But if we want to show analytical things, I think we have to, it should be better than this decoder, I feel, because see, we'll show with respect to ML. Anything less than ML, we want a slightly lower complexity decoder, which achieves capacity for RM. That's a big open question, right? So these are two different threads, quite far apart, I would say. Right? So yeah, see, n square log n seems reasonable as long as it's operating close to capacity. In sense, close to ML. I think n square log n, because we are able to run simulations like, let's say, m equals that 9.2, 10.2, etc., and which already kind of gives you 1024 kind of length, right? See, if we are in the range of 4,000 to 5,000, LDPC codes are the best anyway, right? So the sweet spot for us is always between, around 1,000 or less. But there, I think Reed-Muller codes, if we find a correct decoder, they'll perform, definitely outperform polar codes.
Lalitha?
Yeah.
So studying RPA's performance on other BMS channels.
Yeah.
Firstly, for other BMS channels, is it the same algorithm or do we tailor?
It's slightly different algorithm. So it is dependent on LLRs.
Okay.
right? Because Y can be anything. So
Mhm.
I need to kind of project the LLRs and take it back.
Okay.
But then I need to look at the distribution of the LLRs. We are somehow able to convince ourselves that FHT still works because the LLRs are still independent. Some mean is there, that's fine. They will concentrate around that mean and we'll be able to show the separation. We are still yet to analyze the aggregation step, but it's works with LLRs. So what it works with LLRs is it does a hard decision on the below thing and tweaks the LLR of the above layer. That's what it does.
And what is known empirically?
Empirically, even AWGN, it works well. So because other channels for us, at least empirically, is by AWGN, binary input AWGN channel. It works very well.